In the last video, I showed you what a neuron looked like, and we talked about the different parts of a neuron. And I gave you the general idea of what a neuron does. It gets stimulated at the dendrites, and the stimulation we'll talk about in future videos on what exactly that means. And that impulse, that information, that signal gets added up if there's multiple stimulation points on various dendrites. It gets added up, and if it meets some threshold level, it's going to create this action potential or signal that travels across the axon, and maybe stimulates other neurons or muscles, because these terminal points of the axons might be connected to dendrites of other neurons or to muscle cells or who knows what. But what I want to do in this video is to kind of lay the building blocks for exactly what this signal is, or how does a neuron actually transmit this information across the axon, or really how does it go from the dendrite all the way to the axon. And before I actually even talk about that, we need to kind of lay the ground rules of, or a ground understanding of the actual voltage potential across the membrane of a neuron. And actually, all cells have some voltage potential difference, but it's especially relevant when we talk about a neuron and its ability to send signals. So let's zoom in on a neuron's cell. So let me just zoom in. Right there. I could zoom in on any point on this cell that's not covered by a myelin sheath. And I'm going to zoom in on its membrane. So let's say that this, let me go down here. Let's say that this is the membrane of the neuron, just like that. That's the membrane. This is outside the neuron or the cell. And then this is inside the neuron or the cell. Now, you have sodium and potassium ions floating around. I'm going to draw sodium like this. Sodium is going to be a circle. So that's sodium, and they're positively charged ions, have a +1 charge. And then potassium, I'll draw them as little triangles. So let's say that's potassium. Symbol for potassium is K. It's also positively charged. And you have them just lying around. Let's say we start off both inside and outside of the cell. So let me draw some potassium. I'll just do it as a triangle. I don't want it shouldn't be a time sign. It should be plus. So there's some potassium inside the cell, and then there's some potassium outside. There's a plus charge, and then there's some sodium inside the cell. They're all positively charged. Sodium inside, some sodium outside. Now, it turns out that cells have more positive charge outside of their membranes than inside of their membranes. That there's actually a potential difference. That if the membrane wasn't there, negative charges would want to escape, or positive charges or positive ions would want to get in. So let me write this down. The outside ends up being more positive, and we're going to talk about why. More positive, and we could say less positive. Less positive. So this is an electrical potential gradient. Right? If this is less positive than that, if I have a positive charge here, it's going to want to go to the less positive side. It's going to want to go away from the other positive charges. It's repelled by the other positive charges. Likewise, if I had a negative charge here, it would want to go to the other side. Or a positive charge, I guess, would be happier being here than over here. But the question is, how does that happen? Because left to their own devices, the charges would disperse, so you wouldn't have this potential gradient. Somehow we have to put energy into the system in order to produce this state where we have more positive on the charge on the outside than we do on the inside. And that's done by sodium-potassium pumps. And I'm going to draw them a certain way. So I'm going to draw them like this. And this is obviously not how the protein actually looks, but it'll give you a sense of how it actually pumps things out. So let me draw it like, I'll draw that side of the protein. Maybe it looks like this. And you'll have a sense of why I drew it like this. So that side of the protein or the enzyme. And then the other side, I'll draw it like this. It looks something like this. And of course, the real protein doesn't look like this. You've seen me show you what proteins really look like. They look like big clusters of things, hugely complex. Different parts of the proteins can bond to different things. And when things bond to proteins, they change shape. But I'm doing a very simple diagram here. And what I want to show you is this is our sodium-potassium pump in kind of its inactivated state. And what happens in this situation is that we have these nice places where our sodium can bind to. So in this situation, sodium can bind to these locations on our enzyme or on our protein. And if we just had the sodiums bind and we didn't have any energy going to the system, nothing would happen. It would just stay in this situation. Now, the actual protein might look like something crazy. The actual protein might be this big cloud of protein, and then your sodiums, maybe your sodiums bond there, there, and there. Or maybe it's inside the protein somehow. But still, nothing's going to happen just when the sodium bonds on this side of the protein. In order for it to do anything, in order for it to pump anything out, it has to be it uses the energy from ATP. So we had all those videos on respiration, and I told you that ATP was the currency of energy in the cell. Well, this is something useful for ATP to do. So ATP, that's the adenosine triphosphate, it might go to some other part of our enzyme, but in this diagram, maybe it goes to this part of the enzyme. I'll do it in a different color. So that's maybe our ATP. And then this enzyme, it's a type of ATPase. And when I say ATPase, it breaks off a phosphate from the ATP. And that's just by virtue of its shape. It's able to plunk it off. When it plunks off the phosphate, it changes shape. So let's write this down. So let me write down the steps, just so we remember, and I think it'll help. So step 1, we have sodium ions, and actually let's keep count of them. We have 3 sodium. These are the actual ratios. 3 sodium ions from inside the cell or the neuron. They bond to pump, which is really a protein that crosses our membrane. Now step 2, we have also ATP. ATP gets broken into ADP plus phosphate on the actual protein, and that changes the shape. So that also provides energy to change shape, pumps shape. Now, this is when the pump was before. Now, after, our pump might look something like this. Maybe I'll draw it. Let me clear out some space right here. I'll draw the after pump right there. Clear that out. And so this is before. After the phosphate gets split off of the ATP, it might look something like this. Instead of being in that configuration, it kind of opens in the other direction. So now it might look something like this. And of course, it's carrying these phosphate groups. They have positive charge. It's carrying those phosphate groups. And it's open like this. This side now looks like this. So now the phosphates are released to the outside. So they've been pumped to the outside. Remember, this required energy because it's going against the natural gradient. You're taking positive charge and you're pushing them to an environment that is even more positive. And you're also taking it to an environment where there's already a lot of sodium, and you're putting more sodium there. So you're going against the charge gradient, and you're going against the sodium gradient. But now, I guess we call it step 3, the sodium gets released outside the cell. So here, and when this changes shape, it's not so good at bonding with the sodium anymore. So maybe these become a little bit different too, so that the sodium can't even bond in this configuration now that the protein has changed shape due to the ATP. So step 3, the 3 Na pluses, sodium ions, are released outside. Now, once it's in this configuration, we have all these positive ions out here. These positive ions want to get really as far away from each other as possible. They actually probably be attracted to the cell itself because the cell is less positive on the inside. So these positive ions, and in particular the potassium, can bond at this side of the protein when it's in this, I guess we could call it, this activated configuration. So now, I guess we could call it step 4. Step 4, we have 2 sodium ions bond to, I guess we could call it the activated pump. Activated or changed pump. Or maybe we could say it's in its open form. So they come here, and then when they bond there, it rechanges the shape. It rechanges the shape of this protein back to this shape, back to that open shape. Now, when it goes back to the open shape, these guys aren't here anymore, but we have these 2 guys sitting here. And in this shape right here, all of a sudden these 2 divots, or maybe they're not divots, they're actually things in this big, cluster of protein. They're not as good at staying bonded or holding on to these sodiums, so these sodiums get released into the cell. So step 5, the pump, This changes shape of pump. So pump changes shape to original. Changes shape to original. Changes shape to original. And then once we're in the original, those two sodium ions released inside the cell. And we're going to see in the next few videos why it's useful to have those sodium ions on the inside. You might say, well, why don't we just keep pumping things on the outside in order to have a potential difference? But we'll see these sodium ions are actually also very useful. So what's the net effect that's going on? We end up with a lot more, we end up with more sodium ions on the outside, and we end up with more potassium ions on the inside. But I told you that the inside is less positive than the outside. But hey, these are both positive. I don't care if I have more potassium or sodium. But if you paid attention to the ratios that I talked about, every time we use an ATP, we're pumping out 3 sodiums, and we're only pumping in two potassiums, right? We pumped out 3 sodiums and 2 potassiums. Each of them have a +1 charge, but every time we do this, we're adding a net 1 charge to the outside, right? 3 on the outside, 2 to the inside. We have a net 1 charge. We have a +1 to the outside. So we're making the outside more positive, especially relative to the inside. And this is what creates that potential difference. And if you actually took a voltmeter measures electrical potential difference, and you took the voltage, if you took the voltage difference between that point and this point, or more specifically between this point and that point, if you were to subtract the voltage here from the voltage there, you will get minus 70 millivolts. Minus 70 millivolts, which is generally considered the resting voltage difference, the potential difference across the membrane of a neuron when it's in its resting state. So in this video, I kind of laid out the foundation of why and how a cell using ATP, using energy, is able to maintain a potential difference across its membrane where the outside is slightly more positive than the inside. So we actually have a negative potential difference if we're comparing the inside to the outside. Positive charge would want to move in if they were allowed to, and negative charge would want to move out if it was allowed to. Now, there might be one last question. You might say, well, gee, if this kept happening, if we just kept adding charge out here, our voltage difference would get really negative. This would be much more negative than the outside. Why does it stabilize at minus 70? To answer that question, and these are going to come into play in a lot more detail in future videos, you also have channels, which are really protein structures, that when they're in their open position will allow sodium to go through them. And there are also channels that are in their open position would allow potassium to go through them. I'm drawing it in their closed position. And we're going to talk in the next video about what happens when they open. But in their closed position, they're still a little bit leaky. They're still leaky. They're still leaky. And if, say, the concentration of potassium becomes too high down here, and too high meaning, when they start to reach this threshold of minus 70 millivolts, or even better, when the sodium gets too high out there, a few of them will start to leak down. When the concentration gets really high, and this is really positive just because of the electrical potential, some of them will just be shoved through. So it'll keep us right around minus 70 millivolts. And if we go below, maybe some of the potassium gets leaked through the other way. So even though when these are shut, if it becomes too ridiculous, if we go to minus 80 millivolts or minus 90 millivolts, all of a sudden there'd be a huge incentive for some of this stuff to leak through their respective channels. So that's what allows us to stay at that stable voltage potential. In the next video, we're going to see what happens to this voltage potential when the neuron is actually stimulated.